Oh, thank you. All right. Which long-run proportion of success pi gives the largest standard deviation of the null distribution when the sample size is 10? So, answer is 0.5. So, if we look at our standard deviations, so this is our theoretical curve, the standard normal curve, and every standard normal curve has a center of pi, and the distance from here to here is our standard deviation. And the standard deviation of a theoretical curve follows the formula, the square root of pi times pi 1 minus pi over n. So let's see what happens as the standard deviation changes. And I like to think of this as the square root of the successes times the failures divided by n. So if I have the square root of 0.5, not I, sorry, the square root of 0.5 times 0.5 divided by 10, that gives me a standard deviation of 0.16. So if I do that again, 0.4, if my pi is 0.4, what is the other piece? 0.6, and then we divide that by 10. And what happened? My standard deviation got smaller. Okay, so let's go even farther. The square root of 0.3 times 0.7 divided by 10, and it got even smaller. Okay, let's go the other direction. Well, the square root of 0.6 times 0.4, oh, that looks familiar. What's that going to be? It's going to be the same as the one 2 steps above this, because the 0.6 and the 0.4 have just changed. So the largest possible standard deviation you can get in this case is when your assumed value is 0.5, a coin flip, right? The farther away you get from 0.5, the smaller your standard deviation is going to be. So if I had the square root of 0.01 times, what would the probability of failure be? 0.99, and we divide that by 10, and I get a much smaller standard deviation. Okay, so we could have answered this question without the 10, right? What effect does that 10 have from one standard deviation to the other? None. So that standard deviation, or this question could be answered with 0.5 regardless of any other piece of information. Okay. What is a z-statistic? The value of the statistic? No. The probability of obtaining the value of a statistic, at least as extreme? No, that's called the... We have a name for the second one. What's it called? What is the probability of randomly getting a statistic that is as far as the one that we have found? That's the p-value, right? So when we build our histogram and we cut that end off and we count how many people are in there, is it possible to land in that tail? Yes. In fact, some of our samples did land in, or some of our simulations did land in that tail. So we call that the p-value, and that is the probability of a fair coin landing in this window, which does happen rarely. Is a z-score the standardized statistic? Yes. And is it a measure of how many standard deviations away from the observed statistic it is from the mean of the null distribution? Yes. So both of those. According to statistician Percy Diaconis, oh nice, the probability of a penny landing on head when it is spun on its edge is only about 20%. Suppose you doubt this claim, and you think it should be more than 20%. To test this, you spin a penny 12 times, and it lands heads 5 of those times. So we're going to run that in our one proportion app. So 0.2, how many tosses? 12. And let's do a whole bunch of samples. Why am I using this instead of doing the theoretical model? The theoretical model is easier. I don't have 10 failures or 10 successes. I have 5 successes and 7 failures. That's just not enough. So we draw the samples. And is that a nice normal curve? Not really, right? It's got that right tail on it. So 5 out of 12. What is 5 out of 12? Nobody has a calculator. I do. 0.417. So 0.417. And I want to do greater than, and I get a p-value of 7%. Okay, so the null hypothesis is C. Yes. The null is C, and the alternative is going to be which one? Is this one-tailed or two-tailed? One-tailed. Why? Because it says, I believe that it should be more than 0.2. So this is our H naught, and this is our HA. What p-value is most valid? That's pretty close to what I got, 0.077. Do we have strong evidence that the penny will land heads more than 20% of the time? No. Do we have evidence? A little bit, right? 7%, that's pretty close to 5. So we're a little bit unsure, but we're not enough to say yes. All right. Ooh. In the last 10 heart transplants at St. George's Hospital, 8 people died. Based on this, concerns arose and heart transplantations were suspended to investigate whether the data provide evidence that the long-run proportion is greater than 15%. So we run it. Looks like they did it for us. According to the dot plot produced by the applet, what is the mean of the null distribution? 15.2%. And that came from the summary statistics. According to the dot plot produced by the applet, is the overall shape of the null distribution does it look like a bell curve? No. That is, can the null distribution be described as being a normal distribution? No. So could we use the theoretical model in this case? No, the theoretical model is a nice bell curve that is symmetric, so it doesn't make sense to use it in this case. But we can use the simulations. Recall that to explore more deeply, the researchers went on to look at data from the most recent 361 heart transplants. How did we know that that was the case? Because we only had 8 deaths, which is success, right? We had 8 successes and 2 failures. That's kind of morbid. That's like, have you ever watched a TV show and somebody gets injured and they go to the hospital and the policeman or the doctor say, is he likely? That doesn't mean likely to live, that means likely to die. So only policemen and doctors use a positive to describe a negative. And statisticians. Okay, so 361.71 is our, that is what we're going to use. So 71 divided by 361 gives me 0.19. So I need to change this to 61. Draw the samples. Is that a normal curve? Yeah, that looks a lot better. And then my sample is 19.7%. And I want to shade to the right. What do you think? Point 0.2. Oh, yeah. Let me make sure it asks the same question. 371. Okay. All right. According to the dot plot produced by the applet, what is the mean of the null distribution? Oh, that's why I'm getting a weird number. I still have 0.2 here. And that's why I was confused. Okay. So we expect 15 and we got 19. Is that enough evidence? So 3A is going to be just blank 3, sorry. So 3 is going to be 0.15. What is the SD of the null distribution? It's going to be 0.019. Oh, we could have just done that, right? We have 10 successes and 10 failures. And 5. According to the dot plot produced by the applet, is the overall shape of the null distribution bell-shaped? Yes, it is. So can we use the normal curve? Yeah, we could. So, so why is the null distribution in B a better idea than, the normal approximation better in B than it is in A? Because we have more samples, right? If we don't have 10 successes and 10 failures, it's a bad idea to use the normal curve. It's warm in here. All right. Researchers asked 40 heterosexual couples which person said I love you first. They found that the man said I love you in 28 of the 40 couples before the women did. Because previous research indicates that man tends to say I love you before the woman, we tested to see whether the probability man would say I love you before the woman is more than 50%. So the null is going to be equal to 0.5. So that would be C. And then is this a one-tailed or a two-tailed test? It's a one-tailed because we tested to see whether the probability is more than 50%. All right, can we use the theory-based approach? Yes, in fact, that's easier. We can get by, and the app will always work. It always gives a pretty good idea. But if you have enough of a big enough sample, then you can use the theory approach, and you don't need a special calculator. Just a regular calculator is good enough. So, what is the mean of this normal curve? It always matches up with our null hypothesis. So the null hypothesis said the true value is 0.5. Okay? And our p hat is going to be 28 out of 50, or 40, sorry. So 28 out of 40. Our p hat is 0.7, but we need our standard deviation, which is this distance here. So our standard deviation is the square root of 0.5. I'll get it. The square root of 0.5 times 0.5 divided by, how many people are in this survey? 40. And I get 0.079. So to calculate my z-score, I take 0.7, which is our sample statistic, and I subtract the expected value from the null hypothesis, and we divide that by the standard deviation, 0.079. And that will give me a z-score, 0.7 minus 0.5, divide that by 0.079, and I get a z-score of 2.5. Okay, so get rid of that. Okay, so this says find the p-value. We haven't been using p-value, we've just been using the z-score. If the z-score is 2.5, are we going to accept or reject? We're going to reject. So, and what they're asking is, so if z is greater than, where did we draw the line for a one-tailed test? 1.65. That tells us that p is less than 5. So, do we know exactly what the p-value is? No, we don't. But we know it's less than 5. And we know that means reject the null. And this, again, is a one-tailed test. What if it's two-tailed? How does this sentence change? If z is greater than 1.95, then that means that p is less than 5. And the same is true on the negative side, right? So do we have to double our p-value in a two-tailed test if we're using the theoretical model? No, it's just where we draw the line. So the line is drawn at 1.96. I think it was 6, right? So the same is true on the other side. If z is less than negative 1.65, then p is smaller than 5. And if z is less than negative 1.96, then we also reject. Does that make sense to you guys? Okay. So we have sufficient evidence, or whatever it says, that the long run proportion of times the male says I love you first is greater than 0.5, something like that. What is the z statistic? It was 2.5. What does the z statistic represent in the context of this study? So we've drawn our normal curve, and we landed right here at 2.5. What does that 2.5 mean? I landed 2.5 standard deviations away from the expected value of 0.5. Okay. So that's going to spit out a p-value. And that p-value we decided is less than 5. What does that p-value mean? This is kind of hard for kids to understand. So let's say it was, I don't know, 1.6%. Somebody describe for me what 1.6% means. Anybody get that? 1.6% of what? So, assuming the coin is fair, right? We're flipping a coin, a 50-50 chance. Assuming the coin is fair, 1.6% of all simulations where we flipped a coin 40 times would land that far or more away from the mean. So, how are they calculating the p-value? I'm interested in that. Here's this new app. How nice is that? All right, so 0.5, and my count is 40, and my sample p hat, does this want does this want percentage or does it want count? Well, let's try it. I don't know. Let's see what happens when we do that. It failed. Okay. So 28. 28 divided by 40 is 0.7. 0.7. What am I doing wrong? Oh, geez. Sorry, guys. My sample size is 40. And my count, oh, that's how many I'm doing. So we need to click test of significance up here. And then that will give me my my hypotheses. So pi is 0.5, and then my alternative is pi is, I need to switch that. Okay, now I can see. So pi is greater than 0.5, my sample size is 40, and my count is 28. There we go. Okay, so this gives me a p-value of 0.0057. All right. So what does that p-value mean? Okay, so B. The probability we would see results at least as extreme as the observed statistic is less than 1%, assuming the null hypothesis is true. So is it possible to flip a fair coin 40 times and get 28 heads? Yes, but the probability of that happening is about 0.5 percentage point. Okay. Without using an applet, determine the value of the theory-based normal approximation p-value if we use a two-sided alternative hypothesis. What is that going to do if we, instead of saying greater than, what if we said equal to or not equal to? It's just going to double it, right? So our p-value on the right side is 0.0057. If we turn it into a two-tailed, we have to add over here, which is also 0.0057. And we would add those together to get about 1%. So blank 6. There it is, 0.0114. Okay. We want to see whether players start with scissors, long run proportion is different than 0.3. Okay, so the null, so A is going to be the null, and is this one-tailed or two-tailed? So it says different than 1/3, so our alternative is going to be D. Okay, so this is the null and this is the alternative. Okay. All right, so we want to do a test of significance, and we need to change this to 0.33, and then change this to not equal to 0.33, and our sample size, don't remember, 119, and we ended up with 14 scissors. Okay, so we played 119 games, and we ended up with, what did I say, 14? 14 scissors. That gives us a p-hat of 0.1176, And my p-value is what? Well, look at my z-score. The z-score is negative 4.93. How likely are you to be 4.93 SDs away from the mean? Very unlikely. In fact, the p-value in this case is 0. It's so small it doesn't even register. All right. So, is there evidence to suggest that players start with scissors is different than 0.33? Oh yes, definitely. Different than 1/3. So again, this is going to be A and D, A and D. And how many rocks did we have? So it's the same calculation, but we have 39 rocks. So we change the count to 39, and we calculate. My standardized statistic is negative 0.05. How likely are we to be 0.05 units away from the mean? Very likely, and a p-value is 96%, which is a little bit bigger than 5%. So do we have evidence to suggest that rock happens something other than 33% of the time? No. We do not have evidence to reject the null. Okay. Do voters make decisions based on a candidate's facial appearance? Researchers had people determine which of the two candidates to the House of Representatives in 2004 had the more competent face. You know what this means? People like me and Jacob are in trouble. They then looked to see whether the one with the more competent face won the election. So pi is going to be 0.5. And is this going to be one-tailed or two-tailed? How do you win an election? You get more than 50%. So is this one-tailed or two-tailed? One-tailed. We only want the right side. So A is going to be our null, and B is going to be our alternative. So we ended up with 189 out of 219, or 279, sorry, and that is 0.68. So our p hat is 0.68, and our number of trials, or no, our sample number is 279. So let's plug that in here. So we need to change this to 0.5. And then we want this to be greater than 0.5. And this is 279. And then the count is 189. Well, we get a z-score of 5.9. How likely is a z-score of 5.9? Extremely unlikely. So, does this theory seem to work? How much evidence is there that the most competent looking candidate wins the more than 50% of the time? What are my options? Very strong evidence. So Jacob, if you run for an election, don't put your face on the posters. That's what we've learned. Deal? Just your name. Jacob Erickson for Congress. Leave the poster off. Leave the picture off the poster. What? Oh, sorry. One of the authors used to have an electronic Yahtzee game that he played frequently. The game would roll 5 virtual 6-sided dice but were the dice fair? It seemed to the author that the sixes showed up more than what they should have if the dice were fair, and he wanted to test this. He had the machine roll 500 dice and obtained 92 sixes. So how many sixes should he have got? 1/6, right? Which is 0.16 repeating, or 0.1677. So the parameter is going to be 1/6. The long run proportion. Okay. So this is the parameter which we believe to be 0.167. Okay, so the null is going to be A equal to 0.167. And is this one-tailed or two-tailed? Look back at the original problem. It seemed to the author that sixes showed up more than what they should if the dice were fair, and he wanted to test this. One-tailed. Okay, so is that what they ended up picking? Because technically you shouldn't look at that, but you know how we are. 2A. I don't remember which question it was. 2A, okay, and then 2B. Yep, okay. So yes, this is the alternative. All right, let's run the test. So 0.167, and we ran 500 rolls, not 2,500. So 500, and our sample count is 92. And you can either put in the p-hat percentage or the count. These two calculate each other. So if we calculate that, we get a p-value of 0.15. So going back here, we have little to no evidence that the long run proportion of times the sixes rolled is more than 0.167, or something like that, whatever they say. For little to no evidence. It also seemed to the author that ones showed up less often than how they should if the dice were fair. So the parameter is going to be B, the long run proportion of times 1 is rolled. And then A is going to be your null. And then C is going to be your alternative. So, and that was 72. So let's go over here and change this to a less than. And change our count to 72. Calculate. So we get a p-value of 0.08. What do we do with 0.08? We get nervous, but do we reject the null? No, we reject the null when it's less than 5. So this is probably one of those moderate. So 8A. So we have moderate evidence to suggest that the long run proportion of times 1 is rolled is less than 0.167. So we're starting to think, yeah, maybe the computer has got a bug in it, but not enough to jump in and say, yeah. Interestingly enough, no computer can truly spit out random numbers. Like on these calculators, or you could type in Google, give me a random number from 1 to 7. Okay, those numbers are not random. How would you tell a computer to spit out a random number? Well, it has to follow some sort of programming, right? You can't just say pick a random number. The computer doesn't know what that means. It has to calculate it. So random number generators don't really exist on computers or calculators. So there is a function on this calculator where I can say random number, and I can tell it give me a random number from 48 to 75, and it will spit out a number, and I can just keep hitting enter and it'll spit out a number. But the way it works is every time you turn on something electronic, it starts a clock, and it knows how long it's been turned on. And so the random number generator in your computer or in your calculator or on your phone, it takes whatever time it is, and then it multiplies that by the last 25 numbers that have been put in the calculator, and it generates this huge value, and then it searches through that value until it finds the first number that fits your criteria. So let's say the calculator has been on for 1265 seconds, and the last numbers you typed in were a 4 and a 72 and a 36 and a 19.1, and it multiplies this massive amount of data together, and then it gets this huge number that goes on and on and on and on, and it said, okay, you want a random number between 1 and 100. So I'm going to search through this list until I find it. Oh, there it is, 46. And that's how it generates random numbers. Now, that's not truly random, right? True random number generators, there are people, this is no lie, there are people that sell random numbers to companies who need random numbers. So there was a guy who built this machine, and he had these little cups that had a dice in it, like a 10-sided dice. And there were 100 cups on the wall. And every cup had a camera pointed at it. Or I guess it would have been from the top. A camera pointed from the top, and he wrote a computer program that could look at a dice and count how many dots were on the dice. And so he had a machine that would go over and it would shake the wall so all of the dice would vibrate, and then it would stop. And those 100 cameras would read the 100 numbers and put that information into his computer. And so Google would call him up and say, hey, I need 100 random numbers. And the guy says, great, cost you $700. Google gives him $700. He emails 1 million numbers to them, and then they use that as random numbers. And so every once in a while, he'd just tell the program, generate 10 million random numbers. Might take 4 days. The system shakes the dice, reads the numbers, puts them in the computer, shakes the dice, reads the numbers, and does that over and over and over. Another way to generate random numbers is if you have a container and you suck out all of the air so that there is nothing inside there, well, the universe is made up of energy. There's energy flying around all over the place. Well, sometimes that energy will convert itself into matter and antimatter. So inside this empty space, there's energy flying around, and if it hits itself just right, it will turn into an electron and an anti-electron, and then they slam back into each other and turn back into energy. Well, that process is random. So if you put enough speakers inside there, then using sound, very, very, very sensitive microphones, not speakers, microphones, you can measure where the location of that matter, antimatter occurred. And that's random, and you can turn that into a random number, and then you can sell it to Google when they need random numbers. But if I asked you to write down 100 random numbers, 100 coin flips, heads and tails, you would see obvious patterns in your results. If you tried to fabricate the results, it's super easy to tell that you did not make it random, which is interesting. So when somebody tells you generate a random number, there really is no such thing as a simple random number generator. Okay, not that you guys wanted to know that. Which sample size gives the smallest standard deviation? When sample size goes up, standard deviation goes down. Okay? If sample size stays the same, which value of pi will give you the largest standard deviation? 0.5. 0.5 is as big as it can get. If you get away from 0.5, your standard deviation gets smaller. All right. So 205, 93 happened. What is our pi value? 1/3. And we want to know, do we have convincing evidence that a larger proportion of cardiac arrests occur on Mondays? Isn't that sad? My grandma was on dialysis for 14 years. Every Monday, Wednesday, and Friday, she'd go into the doctor. They would hook one needle into one arm, suck her blood out, clean it, stick it in the other arm, and she would just sit there for 3 or 4 hours while the machine cleaned her blood because her kidneys didn't work anymore. So the distance from Monday to Wednesday is only 2 days. The distance from Wednesday to Friday is only 2 days. But the distance from Friday to Monday is 3 days. So they wanted to know, does that extra day of having dirty blood cause you to have more heart attacks? So the null is going to be equal to 0.33. And is this one-tailed or two-tailed? Larger probability. So that will be our alternative. Give the value of the statistic. So that's going to be 93 out of 205. So that is 45%. Are the validity conditions met? Do we have enough? What are the validity conditions? Do we have 10 successes, greater than 10 successes, and greater than 10 failures? Yes. And in this case, success means they died over the weekend. Yeah, that's success. So, if we do a simulation-based approach, what do you get? So, let's do a simulation. So 0.33, and what was it, 202? What are our values? 205 and 93. So 205, draw my samples, I want greater than, and, oh, I forgot, 90, what was it? 93. So as extreme as 93, and I get a p-value of 0.02%. Pretty small. So let's do the same thing here. So this is 0.33, and switch this to greater than. My sample size is 205, and my count is 93. And I get a p-value of 0.01%. That's pretty close, right? All right, so blank 10. Choose the p-value. Why doesn't that make sense? Did I do something wrong? No? What does 11 look like? Part A. Oh, 10. Okay, so we want 10D. Thank you. I don't see a D. So are the conditions met? So blank 9 should be a yes. Okay, and then 10. I didn't get anything close to that. Your options look different. It should be like 0.002. So 0.00. What are the options? What one's the? Yeah. So that's what it should be. And then did you get the same thing for 11? Something like that? Okay, I don't know why it's showing the wrong answers to me. Okay, so 12A. Okay, something's fishy. Oh, I'm on the wrong one. Come on, guys. All right. There we go. So, 4, I just scrolled down too far. That makes sense. So 4 is less than 0.001. 5 is 0.0001. And then now we're switching to 65 out of 190. So we change this. So 190, and we change this to 65. And there's my 37%. And then if I change this one, 190 and 65. And there I get 36%. Okay. So those are the answers for 10 and 11. And then 12, there is little to no evidence that happens more than a third of the time on Tuesdays compared to Thursdays or Saturdays. All right, we're almost done. Suppose a friend of yours says she is a 75% free throw shooter in basketball. You don't think she's that good, and you want to test. She makes 18 out of 30. Are the validity conditions met for a z-test? Yes. She has 18 successes and 12 failures. Suppose 10 coins are flipped and the proportion of heads is recorded. The process is repeated many, many times to develop a distribution of these sample proportions. What is the predicted mean and standard deviation? So we expect 50%. And how do we get the standard deviation? We take the square root of 0.5 times 0.5 divided by 10. So the square root of 0.5 times 0.5 divided by 10, and I get 0.158, which is a little weird because we haven't met the validity conditions. Anyway, but that's what they wanted. What is calculated using the formula statistic minus mean of null distribution divided by the SD? That is the z-score, not the capital Z-score. How did that look on your end? Was it just blank? Oh, so the answer is just Z. Okay, that is it for today. You may go back to sleep.